Anyway, we can just start the lecture. So, as always, just to guarantee that you guys can hear me and that I'm not talking to myself, would love to just see hello or hear a hi or something in the chat or on audio. Okay, good morning, Olivia. Thank you, Amelia. Good morning, Peyton. Got it. Thank you so much. Okay, so what we're going to do, let me start sharing my screen again and bring this back up. Okay, so we got a really nice question from the audience last time about this kind of counterintuitive, and I agree it's counterintuitive. It's not what I would expect if I was just walking in and looking at this for the first time. Why does placing a dielectric between the plates of a capacitor increase the capacitance? You're putting a dielectric in there, shouldn't it make it worse? You know, why is this actually improving things, or why is this a desirable situation to put a dielectric in a perfectly good parallel plate capacitor? So what I'm going to do is I'm going to just briefly go over this. This is nothing you guys have not seen anymore, but when I first introduced this, I kind of skimmed over the derivation because, you know, anyway, but now we're curious about why this is happening because, hey, it doesn't make much physical sense. Why is it happening? So none of these equations are new. This is all stuff that you've seen before. Our old friend, I'm just checking here something. Okay, our old friend, the parallel plate capacitor, it has a charge on one plate, the opposite charge on the other, and the behavior, the Ohm's law type rule for this configuration is Q equals C delta V, right? And I don't know what the name of this equation is, but to me it reminds me of Ohm's law, so I call it like cousin Ohm's law. I don't know. But it's the governing equation for capacitors. We have this potential difference between the plates, and then I come along and I stick an insulator in there. Why does the C get larger? So I'll try to address that today. Let me go back to our simplest situation. Our simplest situation is we have a parallel plate capacitor with no dielectric, nothing in it but vacuum inside, and it has a uniform electric field pointing from positive to negative, positive to negative, positive, negative, and we have nothing but vacuum in here. The governing equation for this is E equals Q over epsilon naught A, where Q is the charge on either of those plates. A is the cross-sectional area of these plates. Remember, I'm to think of these as two parallel plates. I'm looking at them head on, but they actually have a cross-sectional area. That A is that cross-sectional area that, you know, signifies the transverse dimension of these plates. And that equation we've seen back from chapter 20. And we also have another equation which relates the electric field to the potential difference across those parallel plates. And that's simply that the electric field is equal to the potential difference divided by D, right? With the vector, in both of these equations, the vector nature of this is governed by the fact that the electric field goes from plus to minus. Okay, I just got a message from Jason. Jason, absolutely, that's absolutely fine. Okay, so these are our two equations for the electric field, and all I'm going to do is set them equal to each other. There's two expressions, they're equal to each other, they're both equal to this uniform electric field. So I set them equal to each other, and I solve for Q. And again, this is nothing you guys haven't seen. This is something that we did together once or twice already, which is just take this jumble of constants here and call it C. That's the definition of the capacitance. So the capacitance is equal to epsilon naught A over D in a vacuum. Now, what I want to think about is what happens when I introduce this dielectric in between the two parallel plates. And what happens, you know, for me, it's easier to think of this starting out with a simple molecule. I take one molecule of a dielectric, and a dielectric just means something that is an insulator. It's not a good conductor. So let's say this is a little blop of Teflon. a molecule of Teflon or something like that, and I put it in that parallel plate capacitor in the space between it. It has a large electric field that's going from positive to negative. And what's going to happen is it's going to create a force on the positive that wants to get away from these positive charges and towards these negative charges. And it's going to apply a force on any negative charge in there, and that's going to want to get to this side and away from that side. So this piece of Teflon is going to be overall charge neutral, but when I put it inside this large electric field, it's going to cause a small charge separation between the positive and negative within that molecule. We're talking tiny, tiny stuff like microns or nanometer type deviations, just a small little separation. But that molecule gets polarized. And what happens, we get this tiny charge separation as it's polarized. It's still overall neutral. We haven't changed that this is a dielectric, that it's still, a poor conductor of electricity, and overall the net charge is zero. But the positives are ever so slightly moved to the left, and the negatives are ever so slightly moved to the right. And that is going to induce a small electric field just from that charge separation. As it's separate from this big electric field due to the parallel plate capacitor. We have this small electric field due to the separation of charges inside. So it's a little bit complicated to keep track of, but oh well, we have a big field and we have a little field. Now, instead of one molecule of Teflon, let me put a whole slab of Teflon in there. And what's going to happen is each one of those molecules is going to have this little polarization where the plus goes over towards this direction and the minus goes over towards this direction. And overall, each one of these is going to happen. The net result is that we'll have a little bit more positive charge on the left-hand side of this slab of Teflon and a little bit more negative charge on this side of the slab of Teflon. And we get this overall opposing electric field that points in the opposite direction to the capacitor electric field, which is going in my graph from right to left, from the positive charges to the left to the negative charges on the parallel plate capacitor. And this one's going to oppose it. So what's the net effect? You guys can do addition and subtraction just as well as I can. This induced electric field in the dielectric opposes the capacitor field. It's going to reduce the overall electric field between the capacitor plates. So the net result of this is that the electric field is weaker than it was before there was any dielectric. In other words, the electric field decreases. I put this slab of material in between the plates of my capacitor, and the electric field reduces. So let me see if this is a demo that we've seen a couple of times. I have electric field pointing from positive to negative, and I have my dielectric, which is overall charge zero, has equal number of positive and negative charges. So I take this, I put it inside, and watch a little bit more carefully this time what's happening to that dielectric. The dielectric ever so slightly is getting polarized, where the positives are a little bit more in this direction and the negatives are a little bit more in this direction. And we get an overall electric field in the dipole that opposes the initial electric field of the capacitor. So that's going to make the electric field inside the capacitor smaller. And again, you should ask me, why do we want to make our electric field smaller? What's the point here? So the electric field decreases, but we also have this nice simple equation back here, which I reminded you from before, this simple relationship between electric field and potential. So if the electric field has decreased, the distance between the plates isn't, this dielectric isn't doing anything to the distance between the plates. That stays the same. So my potential also decreases when my electric field decreases. But putting an insulator in between these two parallel plates does nothing to the charge on the plates. The charge is still the same. There's no conduction of charge from positive to negative. There's no path for it to get through. This is an insulator. There's no conduction there. So the Q stays the same. Now we go back to our cousin of Ohm's law, and Q equals C delta V. Well, if Q is staying the same and delta V is decreasing, the only way that this is going to be able to absorb this is if this number gets larger. So we throw this response of the dielectric, this kind of counteracting electric field that's going the opposite way of the capacitor electric field. This response that then overall changes the electric field inside into this capacitor definition, this capacitance definition. And, we say that C must increase. If this decreases and this is staying the same, this has to increase to make up for that. So a little bit of a hand-waving derivation here, but I think it gets to the physical reason of what's happening, why the capacitance increases when we insert this dielectric. And that increase is basically manifests in this multiplicative factor, the dielectric constant. So this amount of increase that's going to, tell us how strongly this parallel plate responds to an applied potential difference, it manifests in this dielectric constant K, which is just a dimensionless number, 1, 2, 3, 4, 5, 6, 7, 8, 9, some number. And the amount of how large that is going to depend on the properties of that dielectric, and in particular, how easy or how hard it is to polarize those little buggers inside from the applied electric field. So I appreciate that question from last class, and I hope that addresses the confusion or the curiosity of what was going on there. Okay, but again, nothing new here. This is just a little bit of maybe a more physical and intuitive understanding of the equations that we've been playing with for quite a while now. So what I want to do now is kind of move. We're trying to see these biological applications of potential. And as a preface to this, I know that I have a lot of biologists in the class. I know people in the class have a good biology background. Some don't. I appreciate that also. And before I get into this, we're going to talk about a lot of, crazy jargon that has nothing to do with physics, like fibrillation and axons and dendrites and all this kind of crazy stuff that, we've never talked about before. But in the end, the physics that I'm applying to these complicated, very complicated structures is nothing you guys have not seen before. I promise you that. I hope that I don't lose you in the jargon, and if I do, just throw up your hand and stop me. And we get a comment from the Francis. Okay, so this was actually Francis's. That's hard to say. Francis's. It was Francis. It was your question, Francis, from last time, and I appreciate if that clarified for you. Thank you for the excellent question. It made me think about this a little bit more, and I appreciate that. I always enjoy to do that. I normally go by Fran. Okay, this was Fran's question. That's a lot easier on my tongue to come to speak. So getting back to this, the biological applications, I'm just trying to show you that this physics stuff, we can apply this to very complicated systems, and hopefully, make sense of it with fairly simple equations. So that's just my preface, that I don't want to leave any of you in the dust. If you haven't seen any of this, my biology background is miserable. I haven't looked at any of this since college, but the physics all of us together have seen before over the last couple of weeks. So I don't want to lose you. Make sure if I do that you stop me. Okay, we get a comment. Oh my God, dude. I don't know. Yeah. Oh my God, dude. So what I want to talk about first is fibrillation. So heart muscles twitch randomly during a fibrillation. This is, I know we got some EMTs in the class, and I appreciate that. You guys probably have seen this happen, or hopefully, hopefully you haven't seen it happen. But what can happen is the heart, it's an electrical device. It's pumping, it's following electrical impulses, and sometimes it just gets out of whack, right? And it can start twitching randomly and stop pumping blood. And that's bad, right? Because if blood stops getting to your brain, within a very short time, your brain is starved for oxygen and you die, right? Or you have a stroke, or it's not going to be a good day for you. So sometimes this is not always, on TV, this always works, but sometimes it does work, sometimes it doesn't work. You see this very dramatic. People come out with a defibrillator. And what this is trying to reset that, that electrical nature of your heart with a rapid passage of current through your heart. How is that done? It's with discharging a capacitor. We know capacitors in this class. We've been talking about them for weeks. A capacitor is a capacitor, whether you call it a defibrillator or you call it, two metal plates, whatever. We know the physics of this very well. So what happens is we're going to discharge a capacitor through the chest, right? Put those pads on the chest and bam, and you get that current through, and hopefully this is going to stop the random nature of the firing of the heart and get it back into a regular pattern. And what's going to happen during this? Well, it's just this same equation. The charge on those defibrillator pads is going to be related to the potential across them by the capacitance. So what I want to do here is hit you guys with a poll. So what I'm thinking about here is I'm not an EMT, but I looked up the numbers for a typical defibrillator and the capacitance. This is a complicated device. I'm really simplifying it down to just the paddles. There's a little bit more under the hood of a defibrillator. But the basic idea is it's a capacitor with an 8 microfarad, that's 10 to the minus 6 farad capacitance. And the voltage across the pads is going to be something like 10,000 volts, 10 kilovolts. So I'm asking you a question in the poll. It'll take me a second to get this going. You can start calculating while I set this up. Those are your 3 answers. We have, okay, so I'm going to launch this poll. We have 4 possible answers. How much charge is going to flow? I have this defibrillator pad, and I'm putting it through someone's chest. How much charge is going to flow in this process? So, okay. 8 microfarads, 10 kilovolts. How much charge actually passes through this person's chest as you're defibrillating them? Okay, I'll give you guys another, 30 seconds or so. It looks like most of you have zeroed in. I've been told that you can change your answer if you think you have the wrong answer. I think you should be able to choose a new one if you want. Okay. So is your answer 80 microcoulombs, 80 millicoulombs? That would be B. Is it 8 coulombs? That would be C. Or is it 8 gazillion coulombs? That would be answer D. And we have 97% of people have voted. So I'm going to shut this down, end the poll, and I'll share the results with you. Okay. The correct answer is B. It is 80 millicoulombs. If I multiply it, what I'm doing is I'm just going back to my cousins of Ohm law, and the charge on this capacitor plate, which is going to discharge when it conducts through your chest, is going to be just given by the capacitance by the potential difference. We have an 8, 10 to the minus 6 times a 10, 10 to the third. So that together gives me a 0.08, I believe, in terms of coulombs. And that is equivalent to 80 times 10 to the minus 3. So, so do we have any questions on that? I got a large percentage of the class chose A, and I'm gotta guess that this is just a misunderstanding of what the SI prefix for micro is. So 10 to the minus 6 micro. This mu. Sometimes my handwriting is not so discernible, but this is supposed to be a mu, 10 to the minus 6, not a mega or anything else. 10 to the minus 6. This is a kilo, 10 to the third. Okay, so if there's no questions about that, we'll move on. And you're always welcome to ask questions at any time, even about something in the past. So if you catch up to me in a moment and you still have a question, go ahead and do it. Just ask the question. I really appreciate your questions. It usually helps direct the class a little bit better, or helps direct my lecture a little bit better. So with the absence of questions or absence of any confusion on that, I think we're hitting about the halfway mark, and I want to get back to what we were talking about last time. So the last time we were talking about this complicated structure, a cell in your body, a neuron or something like that, and under the normal circumstances, this cell, because of the discrepancy in populations of ions in and outside the cell, in particular sodium and potassium ions, we wind up with a potential difference across the cell membrane. And we saw that the cell membrane has some pretty remarkable properties, has a large resistance and a large capacitance. And across this cell membrane, we have this 0 millivolts on the outside and negative 70 millivolts inside. All that matters is the potential difference. We've seen that many, many times. All that matters is the difference. So we have a 70 millivolt potential difference with a higher potential outside than what is inside. What I didn't talk about too much last time was, okay, we saw if this is an RC circuit, then the time constant of this is about 3 milliseconds. And that was pretty cool because it actually, you know, if we compare that to data, if we actually shock a neuron with a small voltage, a small potential difference, and see how long it takes for that potential to die off, the time constant that we would measure in real life is very similar to this 3 milliseconds that we found. The problem that I kind of scooted under the rug last time was the fact that 3 milliseconds in terms of biological processes is not very fast. You really need something, you need a way of propagating information. You know, you think about your body as doing all these wonderful things. I'm moving my hands just because I'm thinking about it. And it's almost instantaneous. It's a very, very fast process. And if I go upstairs and I'm sleepy and I put my hand on a hot pot of coffee, my hand gets jerked back almost, you know, so fast. We need our bodies to react very quickly. And that 3 milliseconds, if that's how long it takes for an individual cell to react, it's just not fast enough. And we know that our body, you know, propagates signals faster than this. So how is it that one cell can react at the level of 3 milliseconds, but we actually have much faster transmission of nerve impulses through our body? And that's kind of the problem that I want to address a little bit today. So the thing that I left out last time is that if I come along and we have our cell here and we have a lot of sodium on the outside and a lot of potassium on the inside, and this potential difference because of the imbalance of ions. What I kind of skimmed over last time is if you bang this cell or you shock this cell or you really give it some kind of stimulus so that it will react, the way that it can react is it has these channels, these ionic channels, sodium channels and potassium channels that can open and close under different stimuli. And what can happen is, you know, here's a little model of what's going on. So I'm only going to show one of the, let's say that these are the sodium plus ions outside the cell membrane. And they're banging around and they're doing their thing and they're doing these kind of random dance outside. And these are my sodium channels that I can open and close. And if something happens that my cell reacts, it can open these channels and all of a sudden I have this large flow of ions through, and I can very rapidly change that distribution of ions by opening, because there is this 70 millivolt potential difference across. So I will have a force, I'll have an electrical force that will kind of impel the motion of these positive ions. So I can very rapidly change the cell can very rapidly change its potential by opening and closing these channels. And that's what we want to examine today. And that process can be extremely fast. So we have ionic flow through these channels. Again, I'm using all kinds of weird jargon from biology. It has nothing to do with physics, and I don't want to lose you on this stuff. For all I know, maybe you guys know about this very well, but I know that there's some people in the audience who are not biologists. Please don't get overwhelmed by this. We're going to wrap this up as basically an RC circuit in the end. So what I'm showing here is a potential in a stimulated neuron. So we know from our last class that the cell or a neuron cell is going to be sitting happily, if nothing's happening, it's sitting happily at negative 70 millivolts. And that goes along, and then something comes along and I stimulate that cell. You know, something happens, I poke that cell, or I shock the cell. Somehow there's an external stimulus to the cell. Those sodium channels are going to open, and the sodium plus ions flood in, falling into that lower potential. We've always talked about potential as analogous to potential energy. When you have high potential energy, you want to fall to lower potential energy. That's a common theme of the universe that we live in, is that if something is in a high energy state, it always wants to get into a lower energy state. We live in a lazy universe. So anytime you're in a higher energy state, it wants to get into a lower energy state. Those sodium ions want to get from that high potential to low potential. So we open those channels, the cell opens the channels, and the sodium plus floods in, and that potential negative 70 millivolts very rapidly changes to a positive, because now we have all these positive sodium ions inside, until it gets to about 40 millivolts. And then the cell, it's very clever, the cell reacts to this change in potential, by opening the potassium channels. And then those potassium, the potassium, which we had an excess of potassium on the inside, all those potassium ions flood out of the cell, and that causes a rapid drop in potential. These two phases, you know, when the sodium is flooding in and when the potassium is flooding out, are called depolarization and repolarization. The net effect over a very short amount of time is that we go from negative 70 millivolts to positive 40 millivolts across this cell membrane. And then the reaction when we open the potassium channels is this repolarization, and it slams back down to about negative 80 millivolts. And then everything stops. All this active opening and closing of the channel stops, and you get kind of normal diffusion of these ions through the cell that takes a long time, and we get this kind of exponential return back to negative 70 millivolts. But this process here can be done very quickly, right? So what's happening here is, you know, we have this rapid reaction of a cell to an external stimulus, a rapid change of the potential across that cell membrane, and then a return to almost where it started very rapidly. And this is much faster than that 3 milliseconds that we were talking about. Once you do this, right, so this is one cell. It's going through this tremendous change in potential. It goes from negative to positive in a very short amount of time. Any cell that's nearby will also react to this change in potential and be triggered as well to do the exact same thing. And then it'll do it to its neighbor, and do it to its neighbor, and do it to its neighbor. So this kind of rapid depolarization and repolarization of a cell propagates neighbor to neighbor to neighbor. And this is called an action potential. I don't know why. I'm not a biologist. It has something to do with potential. It's very, very much like there's a lot of action going on here. So I guess maybe it's that simple. It's called an action potential. And this is the rapid firing due to external stimulus and a nerve impulse, you know, this propagation of a signal along a nerve from, you know, one part of your body to the other, you know, from your brain to some muscle, is going to be a wave of these action potentials kind of moving neighbor to neighbor to neighbor in a chain reaction down the line. So here's my kind of simple cartoon of what's going on here. We have, you know, the normal negative 70 millivolt potential that we've come to see and understand in a cell. I bang one of these cells, and it rapidly goes positive because of this opening of the sodium channel. And then it rapidly goes back to negative again, but then its neighbor reacts to that, and this kind of propagation of a positive potential can propagate down the line in this fashion. It's called an action potential. So, okay. Okay. So now, again, I'm taking a very, very complicated system that some of you have studied for 2, 3, 4 semesters and simplifying it in something that we're talking for about, you know, 10 minutes here. But basically what our model of what's going on in this complicated structure is, I'm going to simplify this down to, hey, we have a cell body that we talked about last time. The cell body is connected by these kind of fibrous things, the axons, that are connected to a muscle. And whatever happens in this cell, we need that to be translated to the muscle, so that the muscle can then go through an action potential and fire and spasm and kind of do something. So either you get a reaction in your hand when you touch a hot pot, or you look at this poor frog that Galvani put on the table and dissected and applied a voltage to, and that kind of the propagation of that electrical signal along the sciatic nerve of this poor frog caused the muscle to spasm and fire like it did. So that's what we're trying to model here, is this kind of behavior, this wave of action potential. So very, very complicated system. I'm going to simplify it in a very basic way. We're going to look at this axon, which connects a cell to a muscle. And when you look at these under a microscope, you'll see that they're segmented. And I trust many of you have actually seen these yourself. They come in these little packs, and each one of the bundles is separated by something called a node of Ranvier. It's a beautiful, very poetic name for what's happening here, but basically we have segments of this long kind of fiber, this axon, and each one of the segments is about 1 millimeter long, and they're separated by parts that are called the nodes of Ranvier. So each one of these parts, I don't know the biology of an axon. I don't know much about myelin sheaths or nodes of Ranvier for that to be, for that matter. But I do know resistors and capacitors, and I know each one of these little packets, each one of these little segments of this axon can be modeled as a resistor and a capacitor in the same way that we did with a cell. Whether it makes any sense or not, we have to leave that to the end to see, hey, does this make any sense in the end? But I can model anything I want as a resistor and a capacitor if it has resistance and capacitance, and they do. So each one of these segments, it's about 1 millimeter long. Again, they're separated by these nodes of Ranvier, and each one of the segments has a resistance of about 25 mega ohms, right? 10 to the 6 ohms, and it has a capacitance of about 1.6 picofarad. So both of these numbers are a little bit different from an individual cell. The capacitance in particular is much smaller than the capacitance we saw for a particular individual cell. But they're a resistance and a capacitance, and they're going to charge and discharge in a characteristic time that is given by our simple RC circuit rule, which is that the tau, the time constant of this system, is just resistance times capacitance. Tau equals RC. Okay? So I'm just looking at a single one of these, segments, and I find out that the time constant of one of these segments, 25 10 to the 6 ohms times 1.6 10 to the minus 12 farads, picofarads, gives me 4 times 10 to the minus 5 seconds. And 4 times 10 to the minus 5 seconds is another way of saying 40 times 10 to the minus 6, or 40 microseconds. Okay, so the propagation speed along this is 40 microseconds. Or I'm sorry, not the propagation speed. I'm getting ahead of myself. The time constant, the characteristic time of each one of these bundles, which is about 1 millimeter in length, is 40 microseconds. That's how long this thing takes to fire and fire and recuperate. So if I want to think about each one of these is going through this weird process, how long is it going to take for this signal to propagate across one of these segments? Well, it's 1 millimeter in length. It takes about 40 microseconds for this to happen. So I go back to my classical mechanics and my definition of velocity, which is just distance over time. The relevant distance here is the 1 millimeter of that particular segment, and the time the time that it takes, the characteristic time is the tau of that RC circuit. There's nothing magical about this number. You guys saw that this time constant is talking about the typical time of exponential decay or exponential growth in one of these RC circuits. So it's not an exact number, but it's kind of gets you in the ballpark of how long it takes for this system to respond. And with that, we have distance over time, 1 millimeter divided by 40 microseconds. So the velocity of propagation of these in my simple model, whether this is true or not is still up for debate. But in my simple model, this is going to take about 25 meters per second for a signal to travel along this axon. Okay, so that's the end of it. That's our predictive power of our model here. Now we have to test this against whether this makes any sense against what we know in the real world. We live in these bodies. We know how fast they react. We know what kind of makes sense. So we want to check whether this prediction makes any sense compared to data. Otherwise, it's a stupid model and we should just throw it away. So my test of whether this makes sense or not is I take a look at my brain, and I don't know why, my brain here has a mustache. I don't know why it came out looking like it has a mustache. I don't know, it's a hairy brain. And it's about 1 meter away from a hand, right? That's about the distance from your brain to your hand. And so that's the distance for a typical signal to have to travel. You come in and you touch a hot pot and you jerk your hand away. It's your hand has to do that, and it's about 1 meter away from your central computer, your brain. So we have 1 meter distance, and we have again, I go back to my V equals delta x over delta t, and I have the delta x is 1 meter. I have my velocity is 25 meters per second. So I have 1 meter divided by 25 meters per second gives me 40 milliseconds. Okay, so this is telling me in this simple model how long it would take for a signal to get from my fingertips to my brain is rough order of magnitude 40 milliseconds. Again, that's fine, but how does this compare to the real world? Well, I had to look this up because I didn't know it off the top of my head, but if you look at typical humans, you, me, and most of the people in this course, our typical reaction time, meaning how fast you can respond to a stimuli, is something like 200 milliseconds. If you are, a top athlete, kind of like an Olympic athlete, or even like a championship video game player, people with really, really good reaction times. And this is rare, but the fastest recorded reaction times that I was able to find was something like 100 milliseconds. Really, it seems like a hard barrier, that 100 milliseconds, for your body to respond faster than that. It does seem to be quite impossible. And it also, just kind of verifying this, if you look at what happens in the Olympics when people are doing races, or when you have a gun that starts the beginning of a race, and then people have to wait until that to react to start. If you react to the gun in less than 90 milliseconds, that qualifies as a false start in the Olympics, and you're thrown out of you're disqualified from the race. So this does seem to be, this does seem to kind of correspond to a real number in terms of what our bodies are capable of. Is something like 100 milliseconds is the fastest reaction time that seems to be recorded in humans. So our simple model here gives us 40 milliseconds. I think that this is within an order of magnitude. And if you think about, I did this from the head to your hand. You could think about, okay, from my head to my toes is more like 2 meters. This could be doubled to 80 milliseconds, and it really kind of gives fairly impressive agreement for this very stupid, simple model of this complicated structure, this axon, cell kind of, and neuron system, that with this simple model, we say, hey, it's an RC circuit, and let's see what happens with this. You come out really with a pretty close agreement with what seems to be reality. So that's our model here for the day. We just got a question from Taylor. do you need to take into consideration the time it takes to charge and discharge the capacitor, so that it should be 1 millimeter divided by 10 times tau? I don't think so, Taylor. I think, you know, that the time that it takes to charge and discharge the capacitor is baked into the number, into the time constant that we build into it. I'm missing where you're going with this. I don't think so. I don't think so, because the time constant that we calculated for the RC circuit, that is the characteristic time to charge or discharge. You know, and when that, you know, let's think of this as a discharge. When that discharge happens, immediately the next cell is going to kind of feel that change in potential and fire and fire and fire and fire and fire. So I think the time constant is what we, you know, what we calculated here. Okay, Taylor, you know, that's my best answer for that. Happy to go further on this if you have any further comments on it, but that's basically what I have on that. We do have a guest from the physics education department, and I'm going to pause. He needs 5 minutes at the end, so let me just pause here. I hit you guys with so much information. I don't want to overwhelm you with it. I want to just reiterate that in the end, we talked about all kinds of crazy stuff here: axons, nodes of Ranvier, dendrites, cells, cell membranes, all potassium channels and sodium channels, and all kinds of things that make my head spin. In the end, all of this just gets back to a few simple equations in our simple model. I don't want to belittle, you know, you could spend 3, 4, 5 semesters learning about this in earnest in biology. But in our simple model, it comes down to a couple of simple equations. This one, Q equals C delta V, and this one, tau equals RC. So we basically baked this all down into an RC circuit and tried to use what we know about RC circuits to apply it to this complicated system. Okay. So I hope you found that interesting. I hope that you found that kind of, I liked it anyway. I like that this kind of simple model can explain some very complicated behavior. In the audience, we have Jason. Jason, are you still here?
Yep.
Okay, Jason, I need to make you co-host, I think, so that you can share. And let me just introduce you. Jason is a member of the physics education department here or physics education division in the physics department. And he's doing a survey of 401, 402 type students. And it's completely voluntary. You're not required to do this. And it's completely anonymous. I'll let Jason take it from here. Please, Jason.
Hey everybody, good morning. I'm Jason. And I'm here at UNH. I'm working on a thesis, on a research on you guys, basically. And what's relevant here, let me share my screen. So what we want to do is basically create a test of some sorts, not for you guys to take, and it won't ever be used to give anyone a grade. It's more for instructors, really, to try to see how well a student has learned a certain concept. I'm focusing it on fluid dynamics, basically how fluids move in a pipe, Bernoulli's, that kind of stuff. And I'm basically asking for your help for a quick research interview, and it'll be used to create some multiple choice questions. And so if you're willing, we will be recording your interview with me, and you'll be just thinking aloud based on the questions I ask you. It won't be formal, it'll be very casual. And due to the circumstances, it'll have to be done via Zoom. And just because of reasons, I have to say 50 minutes at most. Most likely it'll be much, much quicker than that. We'll get through it very quickly. It'll be very tough to try to think about things, physics things for 50 minutes. So. And don't feel pressure to give correct answers. I, for one, am much more interested in the incorrect answers. It'll help me a lot more. So this is your chance to just explain to me or anyone else how you think the world works, especially around fluids. We'll be just studying the data quantitatively and qualitatively to try to say most of the students, like half, 30%, think a certain way. We'll be storing all this data very securely and only share with other researchers and instructors. And none of your name, identifiable data, student ID number, none of that will be saved alongside it. Right? It'll just be what your answers are. And because it's a recorded interview, you have to opt in. I have to ask for your consent. It's normally there to like protect the interviewee from any harm, but nothing like that's gonna happen here. But if you're interested in participating, just email me at that address here. And try to let me know before the first day of finals, so within like a week or so, but that's not a strict deadline. Anytime that you change your mind, just let me know. And if you do opt in, there's a $10 Amazon gift card, but that's pretty paltry. It's more to try to help me out. It'll be really great for me. So if you're interested, if you have any interest, just let me know. And this will be posted on your Canvas page. So if you missed anything or want to get the email address, you can find it there. So yeah, thanks for squeezing me in, and have a great day, everyone. Bye.
Okay, thank you, Jason. And I think we're at the end of the class. So I'll if there's no other questions about axons or stuff like that, I will see you all on Monday for our last lecture. Hang in there. We're almost done for the semester. You guys are doing great, and I appreciate your perseverance through this very weird and challenging semester.